Hey Calc BC, welcome to lesson 6.4, comparison of series. So today we're going to learn two more convergence tests. These ones are both different variations of what we call comparison tests. You can see on the screen here that we are now looking at 10.6 from College Board, comparison tests for convergence. And if we look down at the details, the comparison test is a method to determine whether a series converges or diverges. And we'll look at the limit comparison test, which will also determine whether a series converges or diverges. And as we've talked about, that's really kind of the goal for this unit, is to examine all sorts of different series to determine whether they converge or diverge. So we're just going to add to our arsenal of convergence tests today. So let's switch over to the notes. All right, so here are our notes. Comparison of series. The first comparison test we're going to look at is called the direct comparison test, where we directly compare two different series to determine convergence or divergence. So there are two different setups for this test. If we have some series called B sub n that we know converges, and there's some other series, A sub n, where every term in the sequence is greater than 0, but A sub n is always less than or equal to B sub n, then A sub n also converges. And if we have some B sub n that diverges, and A sub n is always bigger than B sub n, which, again, all the terms are positive of, then the series A sub n also diverges. And I have a little visual that I like to share for why this is the case. So I want you to imagine that there is some B sub n that is going to be a balloon. I'm going to draw it up here. And this balloon represents the sum of the B sub n series. And we know that this converges, right? So there's some finite amount of air in that balloon. It sums to a given number. Well, it's not necessarily given. We don't necessarily know what the sum is, but we know that it's not infinity. So this is a finite quantity of air in this balloon. And if we have some other series, A sub n, where every term is smaller, it's going to be a smaller balloon. So if A sub n is always smaller than B sub n, is it possible that this sum, A sub n, could be infinity? No, because B sub n is not infinity. It's a finite number. A sub n is smaller, so it can't grow infinitely, or else it would like pop outside of the B sub n balloon, right? So if B sub n converges, I'm going to say therefore A sub n also converges. And we could do the same thing in reverse for the second part of this test. So if we have some B sub n that diverges, let's say now we have this smaller balloon, and this is B sub n diverges. If it diverges, the sum doesn't have any bound. So this is an infinitely large balloon. There's infinite amount of air in this balloon. And if we have some other series we're going to compare to that's even larger, so now we have an even bigger balloon. How is a finite sum going to be bigger than an infinite sum? It's not. And there are varying levels of infinity. We'll talk more about that later this year. But for now, we just need to know that if there's some infinite amount of air in this smaller balloon, and we're now studying an even larger balloon, that's definitely going to also diverge. Let me try to make clear that this arrow is pointing at the bigger balloon. Therefore, A sub n also diverges. Okay, so we're still only going to be given one series to look at, but we're going to have to see if we can come up with another series to compare it to. And if we can say whether the first series converges or diverges, then we'll be able to say whether this series converges or diverges if it matches up correctly with the comparison test. So let's try it. So we have the sum from 1 to infinity of 1 over n cubed plus 1. This does not match up with any of our convergence tests so far. It doesn't match up with p-series, doesn't match up with a geometric series, or the nth term test for divergence. So far we would not be able to say whether this series converges or diverges. You could check each of those, but it wouldn't work. So instead, we're going to try this direct comparison test. So I'm going to say that this series is going to be our a sub n. So I'm going to let a sub n, each term of series A, is going to be 1 over n cubed plus 1. What we want to try to do is look within the given series to see if there's anything that we would know how to determine the convergence of. And what I notice is that, what if we drop off that plus 1 in the denominator and we just take a look at 1 over n cubed? That's now a p-series, right? If we wrote it with a sum, this would become a p-series. So we know how to find the convergence of that, and then maybe, just maybe, we'll be able to compare it to a sub n. So let's try that. The first thing I'm going to do is list out that the series for 1 over n cubed is a convergent p-series. And so now we'll have to like define certain series as convergent or divergent within our work to show whether our new series or our original series is convergent or divergent. So we're going to have to kind of get used to that. But if we think about our chart, what was the rules for p-series? If p was greater than 1, it converges. And this p is greater than 1, it's 3. So I'm in parentheses here, I'm going to write it's because p was greater than 1. That way we just know, okay, we showed the reason why that's convergent. And now I'm going to say, okay, well, what can I say to compare these two? And first of all, they're always going to be positive. So I can say 0 is less than or equal to. Which one of these is smaller? Well, this a sub n's denominator is always going to be 1 larger than the b sub n. And a larger denominator means a smaller fraction. So that a sub n actually goes first before the b sub n. So think about this in terms of our balloons. 1 over n cubed was convergent, which is our b sub n up here. And now we have an a sub n, 1 over n cubed plus 1, that's, we just showed, is always smaller. So this balloon has to fit inside of the other one. And if the other one has a finite sum, this one's also going to have a finite sum. So I'm going to write therefore, and I'm going to clarify that I'm now talking about the original series again by writing it out, since we looked at more than one. So therefore, the sum of 1 over n cubed plus 1 converges by the direct comparison test. We always want to say and write out which test we're using. Okay, so there we go. Let's try a couple more. So this second one, the sum from n equals 1 to infinity of 1 over 3 to the n plus 1. This time we are going to declare that a sub n is 1 over 3 to the n plus 2. And similar to letter A, we're going to just drop off the plus 2 and see if we can work with this. And what I would do is just start to rewrite this b sub n so that it looks more like a geometric series. So that's the same thing as 1/3 to the n, which is the same thing as 1/3 times 1/3 to the n minus 1. Now that should look like a geometric series, right? If we look back at our chart of tests, if it's a sub n times r to the n minus 1, well, that's what we got now. If the absolute value of r is less than 1, we converge. 1/3 is less than 1. So this converges We could even find the sum, but we don't need to for this. So I'm going to write out that the sum, this time I'll just write from 1 to infinity of b sub n, since I already defined b sub n over here. I'm going to say that what did I say? Converges by the geometric series test. And in parentheses, I'm going to say y, and that's because the absolute value of r is less than 1. Okay? And then let's now see, how can I relate these two? Well, plus 2 means this denominator is going to be larger, so the fraction is going to be smaller. So we have 0 is less than or equal to 1 over 3 to the n plus 2 is less than or equal to 1 over 3 to the n. And once again, we've shown that since our larger series converged, the smaller one also has to converge. So therefore, the original series, which I'll write out again, converges by the direct comparison test. All right, let's look at one more. Letter C. Okay, so in this one, we are starting at 4 and going to infinity. And that is a little bit odd. It's a little different. But what I will say is that it's going to be important for this. But besides the point, chopping off a couple terms at the beginning of your sum does not change whether it converges or diverges, right? If I have an infinite sum that sums to infinity and I take off the first 3 terms, the rest is still going to add up to infinity. If I have a sum that sums to 5 and I chop off the first 3 terms, that's not going to suddenly now sum to infinity. It's just going to add up to something a little bit less, but it'll still converge. So if we start at 4 instead of 1, that's not going to change that much about how we do this. The point is just that we will still converge or still diverge. And I'll show you why it's 4 when we get there. So first off, we're just going to call this a sub n. And if you're tracking with me here, you should be able to tell that for our b sub n, we're going to use 1 over square root of n, which I'm going to rewrite as 1 over n to the 1/2. And n to the 1/2. So this is a p series. You can tell by the fact that it's 1 over n to some power. And that sum is a divergent p series. And why is that? Because the p was between 0 and 1. Okay. So that diverges. So now we are going to see if we can figure out the order of these terms. And 1 over the square root of n is going to actually be smaller than this, because this one, wait, did I say that right? Hold on, let me track this. Square root of n minus 1. So if we subtract 1, the denominator is getting smaller, which means the fraction is getting bigger. So a sub n is actually larger this time, so we have 0 less than or equal to 1 over the square root of n, less than or equal to 1 over the square root of n minus 1. And now here's the reason that the n equals 4 is so important, because if we have a smaller n, let's see what happens. If we have the square root of 2, the square root of 2 minus 1, that actually kind of screws this up, because this then becomes negative, or at least smaller than this if we have a square root that equals something that's smaller than 1. I might be messing that up. But the point is that whenever n is greater than or equal to 4, this inequality is definitely true. okay? So that's kind of the point here. And that's why we're limited at the beginning, but we don't necessarily, again, we don't need to think about that when we're thinking about the convergence or divergence aspect here, because if you chop off the first few terms, it doesn't change whether we converge or diverge. Okay, so the point is that we knew that the B sub n, which is this one, diverges. So if we think back to our balloons, if this balloon is filled with infinite amount of air, and now we have an even larger balloon, it has to be infinite, right? It can't have a finite sum. So we would say, therefore, the series n equals 4 to infinity of 1 over the square root of n minus 1 diverges by the direct comparison test. All right, cool. So that's the direct comparison test. Now let's take a look at the limit comparison test on the back. So limit comparison test says, suppose a sub n is greater than 0, b sub n is greater than 0, and the limit as n approaches infinity of a sub n over b sub n equals capital L, where L is both finite and positive. If all of these things are true, then the two series, a sub n and b sub n, either both converge or both diverge. So this test can once again prove convergence or divergence. It's all about comparing two series by finding their limit. Now, we know from, for example, Bobo bot needs DC. If we divide and get some constant, what that usually means is that the numerator and the denominator are growing at the same rate. Like it's when the degrees are the same, right? When the exponents are the same. So if we had like x to the fourth on top and x to the fourth on the bottom, we would divide the coefficients, get some constant as what our limit is approaching. So when that happens, the point is that the both of the parts of this fraction, the numerator and the denominator, are growing at the same rate. And it's that same idea here in this comparison test. They either both converge because they're growing at the same rate, or they both diverge because they're growing at the same infinite rate. So we just have to kind of, believe that if we are getting some positive and finite L, that means that these do the same thing. Okay, so that's what's going on here. So let's take a look at letter A. We have the sum from n equals 1 to infinity of this rational expression. And on top, we have an n to the fourth. On the bottom, we have an n to the fifth. I'm going to let that fraction equal a sub n. And we have to come up with some other b sub n to compare this to. And I'm going to choose 1 over n. Now, let me tell you why. Whenever you have a rational fraction like this, what you want to do is compare the first term, or the term that has the degree, the largest exponent, on top and on the bottom. In this case, it's n to the fourth and n to the fifth. What we want to do is imagine that as its own fraction, n to the fourth over n to the fifth. Forget about the coefficients. Just think about the variable with the exponent. And what's kind of, if we start to cancel things out, what's left over? N to the fourth over n to the fifth. The n to the fourths can cancel, and let's just leave us with 1 over n. And the reason we want to do that is because then once we actually divide for this step with the limit, it's going to make nice things happen if we can, cancel everything out except for one thing. So you'll see when we get there, but the idea is that we have a b sub n that's 1 over n, and I know things about that series 1 over n. So if I go n equals 1 to infinity of 1 over n, this is a divergent p series. And that's because it is technically the harmonic series. We take a look at our p series, it's this case, but when p is 1, it's technically called the harmonic series, so we can actually write that in parentheses as our reasoning. Remember, that's the sum, like 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc. it's divergent. Okay, so now what we're going to do is we're going to write out this limit statement with a sub n over b sub n. So I'm going to have limit as n approaches infinity, and I'm going to have this whole fraction on top, n to the fourth plus 10 over 4n to the fifth minus n cubed plus 7 over 1 over n. So that's a sub n over b sub n. I'm going to rewrite this so I can multiply by the reciprocal of the denominator. So it's going to become, again, I have to write limit every time. Limit as n approaches infinity of n to the fourth plus 10 over 4n to the fifth minus n cubed plus 7 times n over 1. And I can distribute that n to the numerator. So we end up with the limit as n approaches infinity of n to the fifth plus 10n over 4n to the fifth minus n cubed plus 7. And now we can use Bobo-Bot needs DC. We have an n to the fifth and an n to the fifth. That's why it was important that we made b sub n 1 over n, because now it made us have two n to the fifths, which means exponents are the same, so we divide the coefficients, so this equals 1/4. And last time I checked, 1/4 is finite and positive. So that is a very good capital L. It's finite and positive. So therefore, our original series, which I'm going to write out again just for clarification purposes, that diverges by the limit comparison test. Okay? All right, so we're going to try one more question. Just to review though, the original series b sub n, 1 over n, diverged, and because this limit of the fractions showed that these two series are growing at the same rate, with a factor of 1/4, but still they're growing relatively the same way. So that means that our other series, a sub n, also diverges. Okay? All right, let's take a look at letter B, 1 over n cubed minus 2. This is starting at 2, but that's not going to play a big role here. Again, it doesn't matter if we chop off the first couple terms. It's still going to converge or still going to diverge, depending on what it did before. So we're going to call that a sub n. This time we're going to make b sub n 1 over n cubed. Now we might be able to do this with the direct comparison test from the other side of this page, but we're going to try this with the limit comparison test. So a b sub n is a p series, and this is a convergent p series. We know that because p is greater than 1. Okay, so now we're going to set up our limit statement. So the limit as n approaches infinity of the a sub n over the b sub n and is going to equal the limit as n approaches infinity of 1 over n cubed minus 2 times n cubed over 1. And that equals the limit as n approaches infinity of n cubed over n cubed minus 2, which equals 1, because we have exponents that are the same, so we divide the coefficients. 1 divided by 1 is 1. And just like in the previous question, we have a L that is finite and positive. We would definitely want to check that and write down in our work that we're showing that, because that's part of the process for this test. And we would say, therefore, the original series from n equals 2 to infinity of 1 over n cubed minus 2 converges by the limit comparison test. All right, because our b sub n converged, we showed through this limit that we have relatively similar series that are growing at a similar rate. So our original series a sub n also converges. And that is the end of the notes. So we learned two new convergence tests. If you take a look at the chart, that's the next two rows. We have direct comparison and limit comparison. All the information is summarized here. And yeah, so that is that. Good luck with the homework. Let me know if you have any questions. Have a great day. Thanks.